Are there any questions? All right. Then we have talked about charges flowing. All right. What is this a symbol for? Which is the positive side, which is the negative side?
The long side is positive.
So if I took a battery and just connected it like that, so the only resistance really is in the wire. Oh, so you okay?
Right, yeah.
Okay. And we talked about before that we have a bunch of electrons over on this side and a bunch of positive ions over on that side, not bare protons, but some sort of positive compound, molecule. I'm not 100% sure what a compound is. I've looked it up. Anyone?
Two things together. Two
Okay.
different molecules.
All right. Some sort of positive compound over there. But it's the electrons that are moving. So I have electrons moving around this way over into here. Now, when they were first developing the electricity, or the concepts and standards of electricity, they realized you had a positive and negative side, that there was a high potential, low potential, and then they went with the analogy of water. Water flows downhill, so they figured that electrical current would flow downhill, and so it was established that current is actually flowing this way. The symbol for current is a capital I. And you can put in parentheses there DC for direct current, which means that the electrons, for the most part, are traveling in only one direction, as opposed to what comes out of our outlets, which is alternating current. And for that, we'll use a lowercase I. I'm assuming that I was chosen because it's straight, kind of like a current. People never saw me enter a river.
So will the current and the electrons always travel opposite directions?
Yes, they will. They did not realize that it was electrons flowing until after these it had been established, and by then they were going to, we're not changing this. If you want to give credit or blame to whoever created this, it was Benjamin Franklin. All right, so we have current flowing that way, electrons flow the other way. Now sometimes textbooks decide, you know what, it's really the electrons that are flowing, so what do we call something the electron current? I'm not particularly fond of that because that only shows, I only see that in physics textbooks at the beginning, and then at some point they just stop calling it that. But someone said that, well, I have current flowing this way, then I'll have electron current flowing the other way. Sure. If you see it in the textbook, they're just talking about the direction the electrons are flowing. Now, what exactly is current, besides flow of charges? Well, more specifically, current is how much charge flows past a certain point in a certain amount of time. So if I have a wire, and I have some sort of, it's not a barrier here, I just have a place in the wire that I'm keeping track, and I count 5 electrons flowing this way, every 2 seconds, I can calculate the current. It's as simple as, well, how much charge was passing by? Well, how much charge was passing by?
The charge, the constant for the charge of an electron times 5.
All right,
And it's every 2 seconds, you have to divide it by the change in that time, 0 to 2 seconds, right?
okay, yeah. What is the charge of an electron then?
Something.
Yes, that is absolutely spot on. Let's see if we can flesh that out a little bit.
It's like negative 1.6 times 10 to the negative something.
All right, we're even closer.
9?
15.
That is 15.
It's something that is just good to know.
That's gonna be on, the test information sheet?
It is, but it's good to know so you don't have to keep flipping back and forth. All right, so the charge of an electron is negative E. This E right here is not the natural log E. This is E for charge of an electron, so negative 1.6 times 10 to the negative 19. Oh, units? Like you mean it.
Coulombs.
Yes. The charge of a proton is just E. Please do not confuse the E's. This is a negative charge. That E minus is an electron. So, therefore, the current flowing across that path would be 5 times 1.6 times 10 to the negative 19 coulombs divided by 2 seconds, and we end up with, let's see, that's 8. So 4 times 10 to the negative 19th units.
Coulomb per second.
Say it again?
Coulomb per second.
Yeah, coulombs per second. Now, physicists look at that and they go, oh, God, it's so much to write. Let's see if we can come up with a shorthand for it. And of course they do. So, they defined the ampere by definition, a coulomb per second. A little bit of a hand wave there. In reality, the coulomb is an ampere second. By definition. And the difference is that officially it's changed with 9 years ago, but ampere is considered a base unit, not the coulomb, and I don't know why. Ampere named after.
Ampere.
Say it again.
Ampere.
There we go. You can put in the accent.
Because that's what you did in the video.
Yeah, no, I appreciate that. There's an accent mark over the first E in the name, and I'm not 100% sure. I don't suppose you know that's the right pronunciation of the E.
No. Well,
Okay.
I didn't look at the spelling of it. I just remember what you said.
Okay.
Yeah. So I could.
Is it French?
If it's
Yeah.
French, then it would be ampere.
Yeah.
So I don't know.
E is log.
It's that way. The graph?
Hmm.
Okay.
That's ampere.
That is an ampere?
No, it's ampere. Yeah.
That's,
Yes.
okay.
You have it right.
All right, so we got the basics of a current. thing really, no, you know what, I'm gonna hold off on that. So if I have charges traveling through a wire, then they don't really travel in a straight line. We pretend that they do. I said we have 5 electrons passing by that spot every 2 seconds, and that could very well be. But that would be a net of 5 electrons. And I also talked about direct current as electrons only travel in one direction. But remember, a wire is filled with stuff. So what the electron's going to be doing is it's going to move along and it's going to hit something and bounce and hit something and bounce, and so it does not travel in a straight line. It has a tendency only to travel in one direction, but sometimes it will hit something and bounce backwards. So what we generally talk about here is we have this drift speed. Oh, by the way, we did come out with a current of 4 times 10 to the negative 19th amperes. Let's go ahead and make that official. 4 times 10 to the negative 19th amperes. Which way is the current flowing?
Well, it depends on which direction we decide, right?
No.
The current?
The current.
That way.
That's right. Yes. Let's not get fooled by the fact that electrons are flowing this way. Yes. Current flows the opposite direction. All right, so we have this drift speed. Now, also, if the electrons are moving, there's got to be some potential difference here. Well, if it's hooked up to a battery, then there's a potential difference between the leads right there, or a voltage. So it's traveling through some potential, which is going to be the higher potential in this example right here. The left or the right?
The left.
Gut feeling, or why?
If all the electrons are going over there, it would.
And
I don't know.
thought your arm was there. You are correct, it is the left side. It's the higher potential. How do you know it's the higher potential? There's more than one way of viewing it.
I know how to say what I'm trying to say, but I can't quite get it there. The opposite of the potential is higher on the other side. And does that make sense? Do you see what I'm trying to say?
I thought I did, and then I veered off. Someone want to translate?
I think I see what you're trying to say. I can explain it any better. How,
What- Sorry, Stephanie?
how I thought of it was that the electrons are being attracted to that side.
Oh, okay, that's one way of looking at it. Was that what you were trying to say, Warren?
Yeah.
All gets to the same place.
Yeah.
Negative charges tend to travel, want to move to higher potential or lower potential?
Negative charges go to higher potential.
Yeah, higher potential. So this is gonna be the higher potential over here. We'll just call this VH and VL. We also know that if the electron is being pushed this way, which way would the electric field be running through that wire? So the electrons are being pulled in this direction or pushed in this direction, however you want to look at it. From a electric potential point of view, we know this is a high side and low side. From an electric field point of view, which way would the electric field be running through the wire, causing the electrons to move this way?
That way.
So I have an electric field going to the right. The electrons like going upstream, or they like moving to a higher potential. Okay. And this is an example of how we started out with force and energy when we talked about the vector and scalar use of this. But we really, when we started talking about the practical, start moving things through, we really talked about the electric field and the voltage instead of force and energy. All right, so I have a bunch of electrons with some drift speed moving off to the left. And so based on this, let's see if we can figure out the current. Now I keep looking at my notes because there's so many little places I could go off, and I just want to, I'd like to limit that. So between hitting things, the electron has an acceleration based purely upon the electric field. We will make the assumption that if I have a current flowing, I got a high side and a low side here, I do have an electric field that we will assume is constant throughout the wire. That's the one. So I know that the force on the electron is going to be equal to charge times the electric field. Sort of do it that way. Which is just going to be the charge of an electron times the electric field. I'm not worrying about the minus sign. We've already sort of thought through the directions. That's got to be equal to the mass of the electron times acceleration. So this would be the equation of motion for the electron, excuse me, when it is sort of in between hitting things. Now, obviously, if it's hitting things, this equation gets messed up because you're introducing another force. But there's not enough information really at this point in order to calculate that. Matter of fact, we're going to hand wave, the physicists hand wave through it. I was about to blame engineers, but physicists do it too here. So if we assume that this object is, on average, running free, except under the influence of the electric field, for some time tau. So I'm going to define tau to be the mean as an average free time. So it is on average the time between hitting things. My acceleration is the charge of the electron times the electric field divided by the mass of the electron. Oftentimes I'll put m sub e for the mass of the electron, but let's just, to avoid writing one more thing, I'll just write mass of the electron. And that way I don't have to worry about the subscripts. So when it hits something, well, it's just as likely to hit it from, I got the obstacle here, it's just likely to hit it from this side as it hits something and comes back and hits it from that side. In essence, what I'm going towards is that, on average, my initial velocity after a hit is 0. The brackets around it are just shorthand notation for average. So if I've got this object that on average is starting at rest, it has an acceleration of charge of an electron times the electric field it's undergoing divided by the mass for a certain amount of time, tau. Well, if I look back at the cake formula, Vf equals Vi plus At. That's an I there. This just comes down to that the velocity is going to be And I'm playing fast and loose with some of the notation here, but that ends up being the drift speed. Questions up to here? Yes?
Is TAL meaning mean free time only in this example you're giving us? Or are we ever going to encounter a scenario where TAL is meaning free time and torsion at the same time? I don't
No,
know if
not
that
at the
would
same
be
time.
possible, but-
I know it's, I know we use tau for torque.
Or that's what, yeah.
Yeah, I don't think we ever used tau for, we needed time when we used tau for both, but if I had to, this is a scalar, torque is a vector,
It's a vector.
so there should be the vector symbol over it.
Yep.
I'm not saying we're not done with torque, but we won't be dealing with mean free path at the time. I assume that was a tear of joy.
Obvious.
All right, so now, I have these charges that are flowing past this particular point at some speed v. I need to figure out what my current is. That's ultimately where we're heading. So, I guess part of it is how many charges could even possibly pass? How many charges are moving? So I'm going to find N as the I want to say free charge. For some reason that I'm not striking these mobile charge.